Okay, so there's a family of proofs that are done that have relationships that are geometric. Sorry, that are geometric relationships that are algebraic. Okay, like here's a couple of relationships, like the length of segment AB is twice AM. Okay, this is a algebraic relationship where one is 2 times the other. Okay, or a scalar multiplier, where the measure of this angle is half the measure of another angle. Okay, that is an algebraic relationship. One is 2 times the other, or one is half the other, or a third, or 7 more than, whatever those kind of things are, those are algebraic relationships. Okay, so there's a family of them where you're going to have to apply some of the principles on that nice little half sheet that I just gave you that will be used in solving these. Okay, so I have 2 of them for you, and you can write the given and the proof and the picture, and then we will proceed through the proof after that. Okay, so in this problem we're given that M is the midpoint of a segment, and we're asked to show that the entire length is 2 times part of the segment there. Okay, so we're going to set this up in your standard 2-column proof with statements on the left and justifying reasons on the right. Okay, always statement number 1 is your given information. M is the midpoint. MDPT is shorthand for midpoint of segments AB. And the reason is it is given. Okay, you are always given some information to start with. If you're not actually given the information but there's a picture, look at the markings on the picture. The markings on the picture will be your given information. Okay, so in this you might be able to say that you are given AM is congruent to MB or something of that nature because the picture is marked. So if you're never given a given statements, look at the picture to see what is marked on the picture. Okay, so back to our reasons. Because M is the midpoint, what do we know is true? What things are congruent because M is a midpoint? Segment AM is congruent to segment MB. Okay? If M is a midpoint of a segment, it creates 2 congruent segments. Okay, so we have segment markings on top and the congruent symbol in between, and this is done by the definition. Okay, it is what midpoints do. Midpoints make congruent segments. So because of the definition of a midpoint, we have congruent segments. Okay, if it's doing what it does, that's its definition. Okay, usually things like this only do one thing. Midpoints only make congruent segments. Okay, so now the next step is to notice that we want to have equals in our proof, but we have congruence right now. So we need a way to change from congruence to equals. Okay, and there is a way to do that. That says if segments are congruent, then their lengths are equal. So how you show that is to write AM without any line on top of it equals MB without any line on top of it. Okay, the line is talking about the actual picture, MB, the segment MB, where this is talking about the length of segment MB. Okay, and we can write that down because of the definition of congruence. Okay? Anytime you are changing from a congruent symbol to an equality symbol, or from an equals to a congruence, you are using definition. Okay? And the reason you know to do that is because you know about congruent segments, but you want to have equals in your proof. So you have to change, and this is how you change from congruence to equals. Okay? Now, we want to have an algebraic relationship, right, in here. So, can you think of an algebraic relationship that exists in this segment? Is there an addition problem or a multiplication problem or something that you can realize, recognize from this picture? Yes, what is it? I think you're all saying the same thing, right? But the length of AM plus the length of MB equals what? A to B. Okay? What is that called where we can add up segments and they equal the entire length? The segment addition postulate, which is why it's addition, right? We don't have a segment multiplication postulate or a segment division postulate. We have a segment addition postulate, which is why it's a plus and not a direct multiplication. Segment addition postulate. Bless you. Okay, so it's looking like something that we want now, right? We wanted to have AB as part of your proof. We've got the AB part. We wanted some AMs. We've got one AM, but it would be nice to have how many? 2 AMs. So how can I change this statement number 4 so that I have 2 AMs? By replacing this MB with AM. Okay, am I allowed to replace this MB with AM? Yes. Sure am, because up above they are equal. And when you replace with equality, you are using substitution. Okay, when you replace with equality, you're using substitution. Now, of course, we've got to write in the rest of this also. I'm just showing you that the MB changed to be an AM. So now we need to write in the rest, because all we've done is we've replaced one part of this number 4 statement. So now that we've done that, we have AM plus AM. What is AM plus AM? 2 AMs equals AB on this side. And is that what we wanted? Sure. I mean, we wanted AB equals 2 AM, but it's the same thing. So step number 6, what did we do to statement number 5 to make statement number 6? We added them together. So this is done by the addition property of equality. Okay, and we've done what we've asked to do. So if you have a midpoint, the entire length is twice one of the smaller segments. Okay, that's only true when we have midpoints, but that is a true statement. Okay, this is an algebraic relationship between these geometric figures. Okay, and they're basically always done like this, the same steps. You use a definition to get some congruence. You change your congruence to equality. You throw in some other type of algebraic relationship, you use substitution, and then you use some algebra or some addition stuff to figure it out. Okay? Number 2, let's look at this one here. Okay, so step number 1 is, of course, writing down your given information that ray BD is the bisector of this angle. Bisector ABC, and that is given. Ooh, I should have written that way down here. Anywho, step number 2. Because we have a bisector, what things are congruent? Angle, this angle, and this angle. Okay? Angle bisectors mean we have congruent angles. So angle ABD is congruent to angle DBC. Okay? That is by the definition of an angle bisector. So definition of angle bisector. Okay, angle bisectors give us congruent angles. That's what they do. Midpoints give us congruent segments. That's what they do. Okay, if it's doing what it does, that's its definition. Okay, so notice we have congruence again, but we want to have equals in our problem. So we change congruence to equals. Okay, perfectly legal to do this. The measure of angle ABD, so that's talking about its degree, is now equal to the measure of angle DBC, its degree. Whatever the degrees are, they are equal. Okay, and this is using, once again, the definition of congruence. We are changing from a congruent symbol to an equality symbol. Okay, here we have an angle thing, here we have the angle measure. Because you want to have equals in your proof, so we need to have equals in our proof. So now once again, we need to determine an algebraic relationship between these angles. Okay? And the algebraic relationship is, that involves angle ABC, the measure of angle ABD, plus the measure of angle DBC equals the measure of the entire angle, ABC. Oops. ABC. Okay, that is just like before when we used the segment addition, only this is angles. So we are using the angle addition postulate. Okay. Yes, these are congruent. We said so here, but the postulate says you can add them up and that equals a larger angle. Okay, and we want to have that algebraic relationship so that we can determine what this is here. Okay, so we have ABD on the left side, so we need to try and get rid of this DBC. Just like before, we can do that using substitution. Okay, so instead of having angle DBC, I'm going to have angle ABD. Because here I said they're equal, so one of them can replace the other anywhere in your proof. So because we wanted ABD up here, we want to have another ABD down here. Okay? What we have used is, once again, substitution. Okay, substitution. So now, just like before, we can add these things together. One of these angles plus one of these angles is 2 angles. Okay, so what we have done is added. So I've used the addition postulate. And rather than having the 2 over here, we're going to move it to the other side. So multiplying by 2 over here is the same as dividing by 2 over here. So what operation have we performed to move the 2 over? We have used division. We divided both sides by 2. So that's the division property. Sorry, not postulate up here. The addition property. Okay? So anytime you have an algebraic relationship, okay, a multiplier or a divider between your things in your proof, you have to come up with an algebraic proof with pluses and minuses. Alrighty then? Alrighty then.